Okay, so this part is about the energy transport and the Poynting vector. So here we define a vector called the Poynting vector. So it's quite important. So it specifies the rate per unit area at which energy is transported. Okay, so the energy like per unit area and per unit time. Okay, so the transport via an electromagnetic wave is given by the Poynting vector. So the Poynting vector is actually given by this S. Okay, so this is the Poynting vector. S will be E cross B and then divided by mu 0. We'll also tells you why it will be like that. Okay, after the size of this chapter. So yeah, so actually related to the energy density stored in the E field and B field. So you can see the 1 over mu naught here, and then E cross B. Okay, so here you can see E. Okay, so we already know that E and B are always perpendicular to each other. So E cross B is with a magnitude of E times B. So the magnitude here is like S equals EB over mu naught. Okay, so this is the magnitude. This is the scalar form. And for the direction is like E cross B will be the direction of S. So very, very simple. Okay, so here it just mentioned that suppose we have a source. Okay, so we have a source generate some EM wave. So it will propagate to any direction. Okay, so of course it is like concentric sphere， 就是应该这些蓝色的应该是同心的球体，只是说它只是平面截面画出来。So actually it's like the cross section of many concentric spheres. Okay, so the cross section will be like of many concentric circles. Okay, so at the very beginning, it's generated by the S, and then the next moment, okay, will be the first ray front, and then sometimes later the second ray front, so on and so forth, and then propagate to different directions. And then here we also introduce something called the density. The density is like I will be ERMS squared over C mu naught. Okay, which is actually like or I should be like the average amplitude of the S. Okay, it will be like E times B over mu naught. Okay, and then here we also know that BM will be EM over CM. Okay, so EM, BM are the magnitude. So if we divide by square root of 2, it turns out to be BRMS will be ERMS over C. Okay, so yeah, so it's like that. So BRMS will be ERMS over C. So here we have so it will be like ERMS, so the ERMS BRMS. Okay, and then it turns out to be ERMS square over C mu naught, which is taking the average. Okay, taking the average of the S. Okay, turns out to be this one. Yeah, so it's roughly like that. And then we also can see from this side, okay, originally if the source generate the power as PS, okay, every single second, okay, generate some energy. Okay, so this power will be PS. Okay, so the density for different radius will be like PS over 4 pi r squared. Yeah, because at the very beginning, all the power are concentrated at the center. and then for different moment it goes to different wavelength as a sphere. So all this power are spread through the whole sphere, so the divided by the surface area, which is 4 pi r squared. So I equals PS over 4 pi r squared, and also I equals E RMS squared over C mu naught. Okay, so here we have a sample problem. So here it says when you look at the North Star, okay, Polaris, okay, Chinese is called 北极星, okay. So you intercept light from a star at a distance 431 light year. Okay, so this is light year. This is not meter. Okay, so yeah, so for the cosmetic, okay, they like to use like AU or even light year. Okay, if it is longer, it can be light year. If it is shorter, it can be AU. AU is the average distance from the sun to the earth. Yeah, and then emitting energy at the rate. Okay, so this is the power, and then that of our sun. Okay, so this is the multiple of the P sun. Okay, P sun is the power generated by the sun for a single second. Okay, and then neglecting any atmospheric absorption. Okay, neglect any loss. Okay, energy loss, power loss. Find the RMS value of the E field, B field when the starlight reaches you. Okay, so here we make sense. Try to make use of the I equals PS over 4 pi r square, and also I equals E RMS square over C mu naught. Okay. So here we need to transfer this out. This is the out. This is the out. But this is in light year, so we need to transfer it back to the SI unit. Okay, so that we can plug in this. Plug it into this formula. So R will be like 431 light year. Okay, so it will be 3 times 10 to the 8. So this is the speed of light. Speed of light multiplied by the time. Okay, will be the distance. Okay, so it will be like 431 year. Okay, how many seconds? In a year, okay, it will be 3600 seconds in an hour, and then every day we have 24 hours, and then every year we have on average 365.25 days. Okay, it is not that accurate, considering some other leap year. Okay, so but at least it is quite close. 365.25. Okay, so it is actually 4.08 times 10 to the 18 meter. So that's why they try to use light year. Yeah, because we always come up with some or 10 to the 18 power or whatever power. Okay, so based on this part, we will be able to solve ERMS. So by moving this part to the left side and then taking the square root, we can have ERMS equals PS and then mu naught C over 4 pi r square, and then taking the square root of the whole thing. Okay, so this is PS is actually this thing multiplied by this P sun. So it is actually 3.9 times 10 to the 26 multiplied by 2.2 times 10 to the third power. Okay, so this is the PS. And then mu zero is actually 4 pi times 10 to negative 7. Of course, you can actually combine these two to be 10 to the negative 6. Yeah, but I just try to remake it there. Okay. So, and then here is 3 times 10 to the 8th power, and then all over 4 pi, and then R is 4.08 times 10 to the 18th power square, and then taking the square root. So this is actually 1.24 times 10 to the negative third. Depends on what kind of SI unit you would like to use, V over M or N over C. Both are correct for the E field. And then for BRMS, it could be ERMS over C. So it will be 1.24 times 10 to the negative third. Let me write that. 1.24 times 10 to the negative third over 3 times 10 to the 8th power. Okay, it will be 4.1 times 10 to negative 12 Tesla. Okay, so this is it. Okay, so this is the ERMS and BRMS that you can sense. Okay, the light from the Polaris, from the North Star. OK， 就是那个北极星，它的光线来到地球的时候，它的 E field 跟 B field 是这么弱的。OK， 4的负3次方，4的负12次方。OK， yeah. So next we talk about the radiation pressure. Just as what I mentioned. Okay, so the EM wave, it has the characteristic of a wave because it is called a wave itself, but also it has a duality. It has also the characteristic of a particle. So radiation pressure is a kind of characteristic of a particle. So here it says, when a surface intercepts the EM radiation, a force and a pressure are exerted on a surface. Okay, if the radiation is totally absorbed, okay, the force is actually F equals IA over C. IA over C. Okay, I don't try to elaborate too much. Yeah, but anyway, so if it is totally absorbed, it is this value. But if it is totally reflects, it will be 2 times. Okay, the idea is very simple. Here we have a, let's say a beam of proton. Okay, hitting something. If it is totally absorbed, of course, so there will be something like IA over C here. Okay, so totally absorbed. So the force will be something like that. But if it is totally reflect, okay, you need to generate something back. Okay, so this is IA over C. This is IA over C again. Okay, so this thing should be like. This thing should be like 2IA over C. So because there comes the IA over C, and then you give it back. Okay, you need to reflect it. So this will be a double. Of course, this is a force. Okay, so this is not that accurate. You can consider that the proton has a momentum. Momentum is P, okay? Momentum is P. Of course, not this pressure. This is pressure. Has a momentum. Has a momentum. So it's like the momentum will change, okay? Will absorb all the momentum, okay? So there will be a force, okay? There will be a force. The momentum change will be like the force, okay, multiplied by the time. So anyway, okay, so we have some forces, okay. If a surface absorbs the EM radiation or totally reflect the radiation, and then we also have something called the radiation pressure, which is the force divided by the cross-section area. So A is the cross-section area, A is the area of the surface. So PR will be like the force over the cross-section area. So the force for a unit area will be the pressure. If it is absorb, okay, it will be I over C. If it is reflect, it will be double, just like what I discussed above. So actually this is the particle characteristic. Okay, particle characteristic. For wave, you cannot imagine. Okay, it just related to the force, but actually for the EM wave, it is actually related to the force. Okay, so we'll say the EM wave has actually the particle characteristic. Okay, so the next part we call it the polarization. In Chinese, we call it 极化. Okay, so the EM wave are polarized. Okay, are polarized if their E field vector are all in a single plane, and all in a single plane. In other words, are like pointing to the same direction. Okay, called the plane of oscillation. So this called polarized. Okay, polarized light. So the light wave from common source are not polarized. That is, they are unpolarized, just as like the sunlight. Okay, so just like the sunlight, or the polarized randomly. So which means that if it is polarized, okay, the E field only points to the same direction. And for the characteristic of an EM wave, the B field are always perpendicular to the B field. The B field always perpendicular to the E field. So which means that if all the E field are in the same plane, all the B field are also in the same plane, but these two planes are perpendicular to each other. So this is the polarized light. Okay, so we will say this is the polarized light. If we try to symbolize it, we can just try to draw it an E field only points to the single direction or in the single plane. Okay. Yeah. So this is the polarized light. Okay. This is the polarized light. This is the unpolarized light. It's like, okay. So the E field can be like, okay, some part like point to this direction, some part point to the other direction, and every direction. So for a quick way to symbolize the unpolarized light can be like, okay, we can just draw one in the vertical direction and the other one in the horizontal direction. So it's like you try to combine all of them together. So of course you should be able to decompose it. Okay, every direction in the horizontal direction and also the vertical direction. So we only have two directions, but yeah, they can span to different directions, so it doesn't really matter. Okay, so these are the definition for the polarized light and unpolarized light, and it tells you that, okay, for the sunlight, okay, and most of the source, it will generate some unpolarized light. So how can we generate some polarized light? Yeah, otherwise, what is the point of defining something called a polarized light? So here we have something called the sheets polarizing axis, okay, or polarizing filter. Okay, I would say polarizing filter or polarizing sheets. Okay, so maybe calling it a polarizing filter may be easier to pronounce. Okay, polarizing filter 就是一个滤波器或者滤光器。Okay, so it's like so here it means that, okay, if we have a polarizing filter like this, and okay, so it means that, okay, if there are some unpolarized light go through it, okay, unpolarized light go through it, after going through it, the lines will only align vertically. Okay, so here we have a equation. Okay, if the original light is unpolarized, the transmitted intensity I is half the original intensity I0, which means that this has the intensity of I0, 就是光的强度是 I0, okay? And then after going through, so this is I equals half of I0, okay? So after going through the polarizing line, the intensity of the polarized light will be half of the original unpolarized light, okay? 所以就是有一半会被滤掉，就是这里就你可以想象，就是有一半是垂直，一半是横的，那所以就滤掉一半 ，okay? Totally makes sense. And here, okay, so here, if we have already some polarized light, okay, if the original light is initially polarized, okay, and the transmitted intensity depends on the angle theta between the polarized direction and the polarizing filter, okay? So which means that if we still have this polarizing filter, okay, only letting the vertical component go through, but the original light has an angle of theta between the polarizing filter and the original polarizing direction, okay? So after going through that, okay, originally it is still I0, okay, but this I0 and that I0 are not the same. For this one, this I0 refers to the intensity of the unpolarized light, but for this one, this I0 refers to the original polarized light, okay? So here, I is the intensity of the light going through that. So I will be I0 cosine of square theta. Okay, so it really makes sense because E field here, okay, will be like, okay, this one, okay, this EY. Okay, only EY can go through, EC cannot go through. So EY will be E cosine of theta. E cosine of theta. So this is EM, and no matter EERMS is also multiplying cosine of theta. But for the intensity, okay, let me recall it here. Okay. For the intensity, it is proportional to the square of the E, okay? So if the E multiplied by the cosine of theta, so the intensity will be multiplied by the cosine square. So this is why, okay, we have this cosine square of theta here. Okay, so this is the two simple equation that we will need to consider for the polarizing light. Okay, so here's a sample problem. So here it says, the figure shows a system of 3 polarizing sheets in the path of initially unpolarized light. Okay, so this, okay, so for this is unpolarized. So let me draw something like this to remind us. Okay, so this part is unpolarized. Okay, the polarizing direction of the first filter is parallel to the y-axis. Okay, so here, this is y-axis, this is x-axis. Okay, so this is horizontal. So this is vertical. This is vertical. Okay, so that of the second sheet is at angle 60 degree. Okay, so here we have a 60 degree. 60 degree to this one. Okay, it doesn't really matter it's going clockwise or counterclockwise. It doesn't really, although it tells you that it is counterclockwise. And then for the third one, it is horizontal, okay, parallel to the x-axis. What fraction of the initial intensity I0 of the light emerges from the 3 sheet system, and in which direction is that emerging light polarized? Okay, so here you say before the sheet 1, okay, it is unpolarized. This intensity is I0, okay, like this. Okay, so after the first one, after sheet number 1, okay, it will be polarized. it will be polarized. The intensity, okay, I1, okay, it is I1. I1 will be half of I0, okay, because originally as unpolarized going through the filter, it will be half of the intensity of the original light. And then it is vertically polarized, okay, because this one is vertically polarized. Okay, so after sheet number 2, okay, it is also polarized. It is also polarized. Okay, so I2 will be I1 cosine of 60 degree square. Makes sense? And then half of I0 will be I1, and then cosine of 60 degree. Cosine of 60 degrees is 1/2. Okay, so 1/2 squared. So it turns out to be 1/8 I0. Also makes sense. And then this will be this is 60 degree. Okay, this is 60 degree. Counterclockwise to the y-axis. Okay, something like this. Okay, and then after sheet number 3, of course it must still be polarized. It must still be polarized. So I3 will be I2. Okay, so between this one and this one will be 30 degree, yeah, because the right angle is 90 degree. So between this one and this one should be 30 degree, cosine 30 degree square. So we have this one to be 1/8 I0, and then cosine 30 degree will be square root of 3/2, and then quantity square. So it turns out to be 0.094 I0, and then in x-axis, okay, like this. Okay, so this one just let you slightly familiar with how to make use of those formulas. Wow. Okay. No more. Okay, so here we talk about the reflection and refraction. So I suppose in high school physics, yeah, you should have learned these fundamental optics. Yeah. So reflection 反射，然后 refraction 折射。Okay, so for the reflection, it should satisfy the law of reflection, which means the plane of incident, 就是入射角 okay, the angle of reflection equal to the angle of incidence. Okay, so theta 1 pi equals to the theta 1. Okay, so how to count the theta will be like, okay, so this is reflection should be considered, this is the incident, this is the reflected ray. Okay, so and then this is the material, this is the surface to reflect the wave. Okay, so how to count the incident angle or the reflected angle is like, we need to consider the normal line, So it is the point go through the incident point, and then perpendicular to it, perpendicular to the surface, and then this line will be the normal line, and then this angle will be called the incident angle, and then that one, okay, between the normal line and the reflected wave will be the reflected angle. So theta 1 equals theta 1 pi. Very straightforward. I suppose you should have learned it. Okay, and then for the law of refraction, we call it the Snell's law. Okay, the Snell's law. The Snell's law is nothing but n1 sine of theta 1 equals n2 sine of theta 2. Should be a constant. What is this constant? This constant is the, yeah, again, I'm not sure. Yeah, so should be, yeah, not, should be a constant. Okay, so yeah, we don't need to care about that constant. Okay, that constant is not that important, but the idea here is like, yeah, of course. Here, when we consider the refracted ray, okay, so this is the incident ray, this is the refracted ray, and then also this is the normal line, so this one will be the incident angle, this one will be the refracted angle. So theta 1 and theta 2 should satisfy this, n1 sine of theta equals n2 sine of theta 2. So, and then n1, n2 refer to the index of refraction. 就是叫做折射的指数 ，OK, index, OK, index of refraction. So, and actually this n is actually the c over v, OK, which means that c is the ultimate speed of light in the vacuum. But for other material, the speed of light will be slower, or at least as fast as the speed of light in a vacuum. Most of the time, it will be slower. So this speed of light, if it is always slower than the speed of light, okay, c over v, it will be larger than or equal to 1. Okay, if it is vacuum or air, okay, it will be 1 or very close to 1. If it is other material like glass, water, it will be slightly larger than 1. Okay, so, and then this will be the index of refraction. So this will be this will be the Snell's law. Okay, so so maybe I can just let you know. Okay, what does it mean by the ultimate the speed of light to be the ultimate constant? Okay, because in this course I will not try to talk about the special relativity, 就是那个狭义相对论. Okay, so actually one of the assumption in the special relativity is that the speed of light in any inertial reference frame will be a constant. 就是一个光速在任何的惯性坐标系，它都是一样的。什么意思？它跟你的直觉是很不一样的。就是说，比如说我在这个惯性坐标系，我看到这个光速，我看到这个光速是 c， 但是如果我以一个速度 v， 在前进。然后有一个光，它假如说它是一个真空或者是空气打过来，它当然是一个还是那个 c 的光速。那你在你的 v 这个惯性坐标系里面看到的光速 c 还是 c， 它不会是 c 加 v， 它不是 c 加 v。你在你的惯性坐标系里面还是看到 c 是光速。然后，如果你是反过来的 ，c 追着你跑，然后你用一个 v 再跑，你还是看到那个光速是 c。就算你垂直着它走 ，OK， 你还是看到光速是 c。所以无论你用一个任意的匀速往任意方向前进你看到的光速都还是一样的 c。当然，这个非常违反直觉牛顿力学不是这么教你的，但是牛顿力学只考虑一些速度很低的运动，所以没关系，那就没关系。但是它只要跟光速挂钩，就是如果你的 v 很小的话，那其实无所谓嘛，因为你的速度跟这个29979245加起来的话，它其实加跟没加一样嘛。但是如果你的速度 v 的话是比如说有个1/10光速的话，那就有差了。你不会出现一个1.1倍的光速你不会出现一个 那它怎么加？或者是如果很靠近光速的速度，它怎么相加相减？但那个是狭义相对论教你的那不是这门课的内容。So anyway, okay, it's a bit out of topic of this course. Of course, when I taught physics 2 to ECE student in the past, I just skip through the chapter 27 and chapter 31. I talked about the special relativity and also the quantum physics. Okay, so that will be, in my opinion, a little bit more complicated, a bit more difficult. Okay, so here we have something called the chromatic dispersion. Chromatic dispersion. Okay, so 就是光学的dispersion called 色散 chromatic dispersion of white light. Okay, so it actually says the blue component is bent more than the red component. Okay, so that's why we can use some trims to so make it like a rainbow from a white light. Okay, passing from the air to glass, the blue component end up with the smaller angle of refraction, and then passing from the glass to air, the blue component ends up to be the greater angle of refraction. So it actually means that, so if it is like air of course have a smaller N1. Okay, so this one N1 is smaller than N2. Okay, so actually it tells you that this is the incident light, and then if I just try to extend it, of course it won't. It will refract. So for the red light, of course it is exaggerate. 它是夸张的，它没有差那么多。只是画得明显一点而已。So it just tells you that the red light, we have a larger angle, we have a larger refracted angle, and then the blue light will have a smaller one. So that it says the blue light blend more. Blend more means that this angle is larger than this one. 它就是转的比较多的角度，转向比较多，但是它跟那个 refracted angle 是相反的。And then here, here we have a N1 is larger than N2. So here it also tells you that. So this red light bend less. Blue light bend more. So red light bend less, blue light bend more. So this is why for the traffic light we use red light to specify stop. Because for the red light it will have less bending. Suppose it is raining, or if it is very foggy weather. So the red light will be able to propagate for longer distance, so that in those situations, you will be able to see the red light rather than the green light. Of course, if you are close enough, you will be able to see both the red light and green light at a certain distance. But if it is far away enough, you may be able to only see the red light rather than the green light, because the red light as the longer with a longer wavelength will bend less. Of course this I mentioned again the figure exaggerate the angle difference. But in a raining situation or in a foggy situation, this kind of refraction will be repeated again and again. So it will accumulate more angle difference into large difference. Okay, so maybe let me